SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome back. Last class we stopped with the functional form of Prandtl-Meyer function. I'll just write it once more. This was the function we had last time, and we said that typically we work with angles in degrees, so this tan inverse should be converted to degrees units, that is all, it is nothing great. Now we will go look at this in functional form on the screen there. What I have plotted here is Mach number on the x axis all the way up to 100, okay, and on the y axis it is angle in degrees. I am starting from m equal to 1. Of course you should know that below m equal to 1 this function is not valid, it is not supposed to have any function value, and you know that it will go complex numbers. Anyways, so from m equal to 1 onwards I have plotted for 3 different gamma values. Okay. What we are seeing here is specifically, let us say we will pick say gamma equal to 1.4, the green one. We are seeing that it starts here, they are all almost the same for very small Mach numbers up to 2 or something, there is not much variation in the angle. After that when I go, they split apart, when you go to higher and higher Mach numbers they split apart reasonably well, but if I look at only gamma equal to 1.4, they tend to become one particular value beyond some point, it tends to become an asymptote, and we gave the asymptotic value last time, we gave this to be 130.5 for gamma equal to 1.4. And similarly we can find such angles for the other cases also, and I believe I gave that also the last class. Okay. Anyways, so now I want to see the effect of gamma in here. As usual we always want to discuss compressibility. We said that changing the gamma is one way of changing the compressibility effects. That is not the only way to change compressibility, this is just one of the ways of changing compressibility. Okay. And I am going to say that gamma equal to 1.67 is least compressible, and as I go more and more it is becoming more and more compressible, that is what I am having here. When I have gamma equal to 1.64 to 1.4, my gamma decreases, compressibility increases. What you are seeing is the Prandtl-Meyer function drops, okay, the functional value drops, that is the change in the function need not be so high to change the Mach number. Mach number still changes. Say I want to go from Mach number say 5 to 10, if I have to do that in gamma equal to 1.3, I have to go from 60 degrees to something of the order of 73 degrees or so, rough estimate, I am just picking up numbers from the plot. Okay. The same thing if I have to do from 1.67 and say I am going from 5 to 10, it has to start somewhere around say 95 degrees all the way up to 125 degrees, rough estimate. Okay. What we are seeing is I have to turn the flow a lot for me to accelerate the flow if I have less compressible gas, gamma equal to a very high value. When I have a easily compressible gas, when I turn it, when I change the flow direction, that is I am sending an expansion fan, when I send it I need to turn it by a small angle to increase Mach number very highly, that is a special effect of compressibility in here. Okay. This is what we have to get out of these plots. So now we will keep these in mind, we will typically have only problems of gamma equal to 1.4 in our simple gas dynamics world, and with that we will get some numerical problems and work on them today. Okay. Let us go to the board again. If I pick a case of, we did this a little bit last time, but I will just give some numerical examples. Let us say I have a smooth corner, smooth expansion corner. and I am going to say I have Mach number equal to 2, m1 equal to 2, and I am going to call this situation m2, okay. And I am given this angle to be 50 degrees. The net turn I am giving for this flow is 50 degrees, let us say. If I give this and I am telling you that this is air, gamma equal to 1.4, okay, we want to find what is the final Mach number I am going to achieve in this. Okay, we gave the formula wise, now we just have to work through with the same formula which we discussed last time. Okay, the way to think about this, I have to find the nu of m equal to 2 here, which is what I will call as nu 1. I have to find nu 1 from this function above, but instead of this function we will go and use tables. It is not easy function to work with, just use tables. Nu of m equal to 2 comes out to be 26.38 degrees for gamma equal to 1.4. Of course, now you know, you have seen the plots, you have to look at for a specific gamma values. For this gamma equal to 1.4, this is the value you are getting. Now with this you remember the formula, right, nu 2 equal to nu 1 plus delta theta, where theta is the angle expansion. How much is that? Delta theta is the net expansion angle. If it is compressing, then it will have a minus sign automatically, it will get a negative delta. Okay. Now I will just put numbers here, 26.38 plus the net change in streamline direction is 50 degrees. So I will add 50 degrees here. Okay. So my final Prandtl-Meyer angle happens to be 76.38 degrees. Now I know that this flow will reach a Mach number such that it will have 76.38 degrees as the Prandtl-Meyer function. So what I have to do is go back to that plot and read out 76.38 what is the Mach number, okay. And instead of doing that from the plot, I am doing it from my tables in compressible flow tables book, and I am getting that Mach number to be 4.95. Okay. What has essentially happened is my Mach 2 flow, when it expands over this corner, has gone to a point where it is having a Mach number of 4.95 here. That is what has happened. I am assuming that after this it is going just straight, it is not changing anywhere. Okay. Now this being said, I have to inculcate the habit of drawing expansion fan the correct way. So let us say till here the line is all straight and this is the first point of change, and let us say this is the last point of change, and since it is a smooth corner, this expansion fan will be spread over this whole region. This is what we discussed last time. Okay. Now I have to say that the very first wave will be at an angle with respect to that local streamline direction such that this will be equal to mu locally. Why? The expansion fan, each individual wave travels at speed of sound locally. So with respect to that local velocity vector, it is going to have that mu value. Remember that it is always local velocity vector, local Mach number. Okay. So for m equal to 2, this whole region is uniform flow up to this first line. So m equal to 2, mu angle will be sin inverse 1 by 2, which is 30 degrees. So it should be drawn such that it is exactly 30 degrees. Since it is not very nice, I will draw it again. We will make it look like it is close to correct. So it is going to be more like this for this particular problem. It should actually be probably slightly lesser. But anyways, this is your 30 degrees, okay, and it is going to keep on going there. What should be the final Mach, not Mach number, final angle of my expansion wave? If I look at it, every expansion wave is like a sound wave. So for that local Mach number, which happens to be 4.95, I have to find the mu for that particular Mach number and find the local velocity direction which will be parallel to the wall here. So I will draw this local direction of velocity vector, and I have to find the local Mach angle for that Mach number, which happens to be mu of 4.95 happens to be 11.66. degrees. Okay. I will use this number, this is sin inverse 1 by 4.95, that happens to be this. Okay. So, with respect to this flow velocity direction, I am going to have 11 degrees from here, which is a very small angle like this. So, from the last point of change, it is going to have an angle like this. Now, I will erase whatever is unnecessary so that it is not confusing. Draw this again. And this, actually I will remove this also now. You know it is 50 degrees, if you want we will mark it here. This is 50 degrees with respect to horizontal line, that is this wall angle. Now, my initial expansion wave line goes like this, final one goes like this. Okay. This is the correct way to draw it. It actually crosses the horizontal and goes below also. For this particular case it does. Okay. What matters is, with respect to the local velocity vector direction in there, I am going to have that 11.66 degrees. This is the last wave. So, overall this final angle with respect to my horizontal will be what? 50 minus 11.66, right? What is that? 40, 39, 38.34, 38.34 degrees. That is what will be the angle below horizontal. That should be the final angle here. Okay. Think about it that way, this way. Now, let us say I want to draw intermediate expansion fans, a few of them. There are so many waves, I said it is infinite number of expansion waves here, in which case I can draw a few more. When I draw others, I have to draw it such that there is a slope change in a linear fashion to some extent. I am assuming that this change is linear, it need not be, but to some extent this angle and this angle must be around this middle angle, or the middle one should be having an angle in between these two angles, it cannot be changing. Just think about it that way. Okay. Every angle should be like that. It is a smooth change in the slope of this expansion. Okay. This is what you have to think about. This is one particular case of smooth expansion. Let us go for smooth compression. Okay. We will keep this, just go for a smooth compression case where I am going to have a wall and it is going to turn to a 60 degree angle. And it is turning into the flow. What does that mean? It is going to block the flow, it is going to decrease the Mach number, so it is a compression wave sitting there. Okay. And I am going to say the incoming Mach number m1 equal to 4, gamma equal to 1.4. We are not currently worried about finding the pressure and temperature, if needed we can do it, we will do it in some other example following this. Okay. How will I work on this problem? Exactly the same way, nu 1 will be nu at m equal to 4, this value you get from tables, that value happens to be 65.79 degrees, nu 2 equal to nu 1 plus delta theta, but by our convention delta theta is the amount of expansion. In this case it is compressing, so I have to give a negative value for this, 65.79 minus that 60 degrees we said, okay, which happens to be 5.79 degrees. This is what I am going to get, 5.79 degrees. Okay. Now, if I go back and look at my table such that nu of that particular m2, let us call this as my m2, nu of that particular m2 happens to be 5.79, that m2 value will be 1.3 Mach number. So, essentially if there is a smooth compression of my flow from Mach 4 up to 60 degrees, then I will end up with a flow of 1.3 Mach number. This is what I am saying. Okay. again I have to go back and think about how to draw these compression waves. It's weak compression waves, so I can still think about it as isentropic, and so I can say that the angle at which it is going to go with respect to the flow will be Mach angle again. If I say it is Mach angle, now I have to find the mu value for this. I will put mu 1 for m equal to 4 is sin inverse 1 by 4, that is 75.21 degrees, and for this case mu 2 happens to be 50.29 degrees. I think there is a problem somewhere. I made a mistake somewhere, I think. It cannot be that you guys have a calculator? Can you check whether this 75.21 is right? I think there is some mistake there. Okay. Anyways, I know that when Mach number increases, the mu angle should decrease. I am seeing that there is a mistake there. This value sin inverse 1 by 4 is 14.47 degrees. Okay, we will use that number, and tell me the same for 1.3. What is this value? This is correct. Okay, good. Now I am more comfortable with this. Okay. So what I am seeing is locally with respect to this flow vector, Mach 4 flow has a Mach angle 14.47, which is a very small angle, subtending an angle very small with respect to this. I am actually drawing it slightly big so that it is easy to visualize. Okay. And then as it goes, Mach number decreases, which means my mu angle should increase. So when I am drawing my local velocity vector like this, with respect to that my mu would have increased. Okay. I am drawing too high probably here. I do not want to draw it this high because the final angle is 60 degrees plus 50 degrees. Okay. So it is going to go somewhere like this, and with respect to this final angle, I am going to say my mu is 50 degrees with respect to that, which means with respect to this I have to draw a 50 degree thing there, which means with respect to horizontal it has crossed 90 and it is coming inward. Okay. Going to go like this. This will be your situation. If I think about a case, it is more like this. Okay. It is going to look something like this. We will not worry about how they interact right now. Okay. This is a very complicated case. When such a thing happens, there is probably a normal shock sitting in front of it. Typically we do not see compression waves running upstream, but we will currently keep it like this. We are interested in studying what is happening only very close to the wall, this region alone, nowhere else, just this region, where whatever theory I have said will be applicable, because it is all very small change at any time, very small changes close to isentropic, so this will work. When I go more out, these compression waves will come together and they will form a strong compression wave which will become a shock eventually. When that point happens, it is non-isentropic, I cannot use any of these relations, things will go wrong there. Okay. So this will be the case here. Okay. Hopefully you will get comfortable with drawing these Mach angles, that is the idea. Okay. Now we will go for another example which is all sharp corners. This is most common example in expansion fan and gas dynamics. I am having a sharp corner change and it is 20 degrees, and the incoming Mach number happens to be 2. It is air, so gamma equal to 1.4, P1 equal to 1 atmosphere, T1 equal to 300 Kelvin. We have this whole thing. Now we are told to find what will be the final pressure, temperature, Mach number, standard things, every property that is needed, P02, T02, everything. We want to find all the properties. So how will I do this? It's exactly same procedure as what we did just before this board, which was find the local Prandtl-Meyer angle, nu at m equal to 2, this is my nu 1, which from tables will be 26.38 degrees, and nu 2 equal to nu 1, this is expansion angle, so it is plus 20 degrees. So the final value is 46.38 degrees. This, if I go and use my Prandtl-Meyer function tables from compressible flow data books, I will get m2 equal to 2.83. This is the first phase. The next thing I want to do is draw that shape there, expansion fan shape, exact shape. How will I do that? What is the first angle going to be? 30 degrees, sin inverse 1 by m1, okay, sin inverse 1 by 2. So with respect to my flow vector, it's going to be a 30 degree line. That is my first. It's really not 30, assume it's close to 30. This is your first line. Okay. Now the next one, for this I have to find mu 2, 2.83, that comes out to be 20.7 degrees. So the final streamline angle is going to be parallel to this wall, which is what is the use of this expansion fan. And so now with respect to that I have to draw a 20 degree line. Okay. It so happens that this change itself is 20 degrees, so I know what my 20 degree looks like. 20.7 will be slightly above this 20 degrees. So my final expansion line happens to be only slightly above horizontal. Since I am exaggerating it, it looks like it is too big. Should not be, it should be almost that horizontal line. Maybe I will draw one more line very close. So this is my set of expansion fans. This whole region is my expansion fan. This is the way to draw for this particular picture. Okay. That is the easy part. Now you have to go and find the pressures and temperatures. How will I do that? Very simple, expansion is all isentropic. So I know my P naught and T naught remains the same. So I have to find P2 equal to, this is the gas dynamics way of writing stuff, so get used to this, P02 by P01 into P01 by P1 into P1. Okay, it's a nice way of writing, pressure equal to something pressure multiplied by a set of ratios. Okay. Now we know that this is 1 atmosphere, remaining numbers we have to find. Since it is an isentropic expansion, I can say that P naught does not change, we did this long back. Okay. It is also T naught does not change. Okay. Anyways, here I will make this 1, P naught does not change, so this P naught 2 is equal to P naught 1. Remaining things is just numbers I have to find from isentropic flow tables. For M2, P by P naught is given in my tables and I used that is 0.0352. Divided by, my tables has P by P naught, so I will do divided by the other value for M1, that is 0.128, multiplied by pressure P1, for us it is 1 atmosphere, so I will just multiply by 1, final answer is 0.275 atmospheres. This is what I have. Okay. Now the same thing I have to do for temperature. Of course, I can just say to you that T2 instead of all P's replace it with T's, that is all you need to do really. Let us say I will just go and do that. T2 will be, I will just do it once more, T02 into T02 by T01 into 1 by T1 by T01 into T1. This is a nice way of writing it for me. And I am going to find this to be 0.384 divided by 0.555 multiplied by 300 Kelvin, and that answer happens to be 207.6 Kelvin. Okay. That is what I have there. Now the remaining thing is finding T02 and P02, that is what is left. not very difficult, it should be same as T naught 1 and P naught 1. We have numbers for all the ratios. Okay, I have T2 by T naught 2 or P2 by P naught 2, or the same thing for case 1. Any one of them I have to use. Let us say I use P1. So P naught 1 is equal to P1 divided by P1 by P naught 1. 1 divided by that number was 0.128, happens to be 7.81 atmospheres. Okay. And similar thing T naught 1, T1 divided by that ratio is 0.555. So I have to multiply this with 300. So 300 by 0.555, that number is 540.5 Kelvin. Okay. And of course P naught 2 is equal to P naught 1, T naught 2 equal to T naught 1. So now I have solved this full problem of expansion fan. Any other property I want, I can find. What other property is important in this problem? Anything else that we haven't talked about till now? Only one more. Happens to be velocity. Okay. So we will just find the velocity also. Why do I have to talk about this? Just in case if somebody has a doubt that Mach number increases, I cannot just say velocity increases because temperature decreases. Okay. I have u equal to m into square root of gamma r t. We know that t decreases, m increases. What happens to velocity? It can go the other way, but we will just check it. It has to accelerate. Then only we can call that the flow is accelerating when it is expanding. Okay. We did this long time back when we were discussing stagnation points and stagnation enthalpy. There we said if my temperature drops, my velocity increases. Right? That should be satisfied even here. So we will just check it. U1 I want to calculate, so I will put M1 was 2 for our problem into 1.4 into 288.7 into temperature was 300 Kelvin. Okay. And this answer happens to be 696.4 meter per second. This exact number we have been using a lot, 696.4. Okay. Because we typically start with Mach 2 problem in supersonic flow. So you will always get that. U2, we found that the Mach number was 2.83, 2.83 into square root of 1.4, 288.7 into temperature we found was 207.6. So if I find this number, it is 289.7 meter per second. This multiplied by 2.83 is my final answer, which is 819.8 meter per second. If I go look at this number here, if I just see the speed of sound here, what will be the speed of sound? I have to divide this by 2, it will be at 348.2. Okay. So my speed of sound has gone down, yes, okay, because my temperature is lesser, it is colder, so it has gone down, but still my Mach number effect is higher. So we are finding that the velocity is increasing. Okay. Even though I am getting colder, my velocity is still increasing. Eventually you will go to a point where if I keep on increasing, if I want to increase velocity, I have to change my Mach number by a huge amount, because temperatures will become close to 0. Then you will have to change your Mach number by a huge amount. There will be a point where you cannot change anymore. What is that point called? The Vmax. Right? We did this Vmax when we introduced T naught. Right? T naught equal to T plus U square by 2 Cp we said, and if I put T equal to 0, you will get T naught equal to Vmax square by 2 Cp. That Vmax will what you will reach. Eventually it will go to a steady state. We have seen plots of this also before. Okay. So this is one problem which we have solved like this. I will give you another case, a little more complex version of this. That will be the last numerical example I think I will solve in expansion alone world. let us say somehow I have a flow that is like this, and here Mach number is 3, gamma equal to 1.4. Of course, I could have done problems with gamma equal to 1.67 or 1.3, is just a change in one number, it does not change so much for us. Okay. Now, I am telling you that this angle is 20 degrees. 20 degrees is the ramp angle, and I am telling that this is parallel to this. So, it is a straight section, and outside is vacuum. That is the setting we have. I want to find what is the flow field here, okay, the absolute flow field. Let us say this is my nozzle exit from my rocket and it is sitting in space. Currently the flow coming out is m equal to 3 at gamma equal to 1.4, and I want to see what is the flow field here. That is the idea. If I think about it that way, what should I do? I will just go faster this time, nu of m equal to 3. I will mark this region 1, this region is 2, and somewhere outside is 3. I will mark this something like this. So, I will just go nu 1 is nu at m equal to 3, happens to be 55.76 degrees, and mu 1 happens to be 19.47 degrees. Okay. Now, nu 2 must be nu 1 plus 20 degrees, because it is expanding, it is plus 20 degrees, which is 75.76 degrees. Okay. So, from here I will get a m2 which happens to be approximately equal to 4.87. I do not have clean resolution at this high Mach numbers in my tables, so I just gave roughly 4.87, I did not interpolate very well. Okay. And this will give you a mu 2 value of 11.77 degrees. Once I know this, I should be able to draw the expansion fan there. Okay. So, I am having 19 degrees, roughly 20 degrees is the angle. We know that this angle we said is 20 degrees, so it should be roughly that. Okay. That is the first expansion line. With respect to the incoming vector, it is 19.5 degrees above. The last one going to be 11 degrees from this wall, which means it should be roughly midpoint is 10 degrees, so it should be slightly above that, so it is somewhere here. This whole region is my expansion fan, that whole region is expansion fan. So, the flow comes here, turns and then goes out straight like this, that is what is happening there. Okay. This is the first case. Of course, now you can go and find P2, T2, every other property you want, U2, whatever. Now, we will go out of that, I believe you can do that remaining part. Now, the next thing is, we have not given any angle change, but you are given pressure outside. We said in gas dynamics there are two types of boundary condition, velocity direction and pressure. We have been using velocity direction till now, suddenly we are giving pressure boundary condition. If I give pressure boundary condition here, what should it be? I have to just go and find what is the pressure here. It so happens that P is 0. Okay. If it is 0, what should be my Mach number? Keeping same P naught, isentropic, should be m tends to infinity. Okay. So, I know that my final Mach number m3, actually I will just put tends to infinity, okay, not equal to, it tends to infinity, okay. Which means now I know my m3, I know my m2, I just have to draw the expansion fan, problem is different. Okay. So, I will find my nu 3. What is nu 3 for gamma equal to 1.4? This number we discussed last class. Okay. That number happens to be 130.5 degrees. And nu 2 we calculated just now 75.76. So, my delta theta, the change in angle of the streamline, comes out to be nu 3 minus nu 2 happens to be 54.74. 54.74 degrees, okay. Which means the flow has already turned 20 degrees from horizontal, it can turn only 54 degrees more. Okay. So, I will erase these things for clarity. can turn only 54 degrees more from here. Okay, this is my 90 degrees, it's 60 degrees, so it can turn only 54 degrees. So the final velocity vector direction is this. Okay, it cannot go any more turning around the body. Okay, it can turn only till here, and this change is 54.74 degrees. Okay, that is this change. Now I just have to draw the expansion fan angle. Okay, my first wave here, what will be the angle for that? My first wave of the expansion fan, what should be the angle for that? The same thing here, 11.77. But we already have an expansion there. I don't need to go and look at it anymore. I know that the Mach number here is all the same, velocity vector direction is all the same. So I just have to draw a parallel line to that. That's my first expansion wave. This and this are parallel. Right, it's the same condition. And the last expansion wave, what is the mu value for that? Sin inverse 1 by infinity. Sin inverse 0 is 0. Okay, so you are going to have a mu angle 0 with respect to flow velocity vector direction. My last expansion frame is going almost on it. Okay, so it comes to a point where it is not physical for us. We already told you that m tends to infinity is not a real situation. By then my continuum assumption breaks down, so I cannot be using this analysis here. Okay, by here pressure is 0 here and non-zero here, that situation will never arise. Okay, and at this particular situation where pressure is close to 0, I cannot apply continuum anymore. It's no more continuum, there is no molecule there, cannot be continuum ever. Okay, so it's just a hypothetical analysis, but one thing it tells is, if I have a case like this, the flow will just go straight like this, it will never try and turn around the body. That is a very important thing you should know. If I start with very high Mach number, it cannot be turned too much already, because it has already turned a lot. Okay, that is the way you have to think about it. And you should of course remember the plot which we just saw, mu of m versus m, it looks something like this, which means if I start somewhere at reasonably high Mach number, say 5, after that I can turn only so much, especially if it is a very compressible gas, I can turn only lesser, because if it is a more compressible gas, it will turn faster. Okay, the curve will become flat very fast. Okay, this kind of effect will happen, which means if I want to turn my flow more, it is probably not possible if it is very compressible flow, but still my Mach number can go to infinity. That kind of situation can arise. Okay, so the next thing we can do is, once you understand these, it's just a simple extension of this. Okay, I will consider a first flow problem, which is I have some jet coming out with a known Mach number and velocity direction. Let us say m equal to 2, and I have to tell you P naught value. Let us say I will give you P1 equal to 1 atmosphere, if such a situation is coming out, and let us say I do not have P exit is equal to, let us say 0.1 atmosphere. If I have such a situation, okay, and let us say I will give you a T1 also 300 Kelvin. If I have something like this, I will just go for how will I calculate this problem. Remaining thing is just going through the tables, not much of use for us. We will just, let us assume that you can do it. I will give you exercise later on the website. Okay. Now we know that Mach number is pressure is 1 atmosphere and it has to go decrease to 0.1 atmosphere, which means the flow has to expand more. Okay. If it has to expand more, because this is the new boundary condition, then it has to have expansion fans. The very first fan will be with respect to this angle 30 degrees, something like this. This angle is 30 degrees. That is the first fan angle. The last one will be decided by what is the final Mach number. Let us say you can calculate all that. I will just draw some angle roughly currently. Let us assume this is correct for now. Okay. But how will I calculate this final Mach number? The flow is turning like this, right? You can imagine that. Flow is going like this and it is turning out. If I think about the same thing on the bottom, it's going to go like this and it's going to turn down like this. This is what should happen. Okay. You have to start getting used to this because we are going to draw more and more of this as the classes come up. Okay, next week or the week after next we will draw more of this, a lot more of this. Okay. And how will I find it? I know the pressure here and I am going to assume this is isentropic, so I know P naught value is same as P naught 1. So I will just go and use Pe by P naught 1. This will give me my M at the exit, M at the outside boundary. Let us call this ambient pressure. I do not want to call it exit, it will confuse you later. Okay. And jet boundary. Mach number at the jet boundary, the final line will be the jet boundary. To find the Mach number, we will go and deal with jets separately later. I am just giving you this one example. Okay. I will find the Mach number. How will I find this Mach number? I am having Pa by P naught, that from isentropic tables for gamma equal to 1.4 is going to give me some Mach number. Once I know the Mach number, I know the delta nu, right. So I know how much it will turn by. This will give me a nu at jet boundary. I know that nu minus nu 1 is my delta theta. So I have to find the delta theta now. I will tell that at the end of it, it has turned by so much angle. Okay, that is what it will come out to be. It will turn by whatever angle it is. I haven't calculated this, but you can calculate it. It's not. It's the same procedure. I have to go follow it again and again. And I will go to a point where I know this. Once I know Mach number, I can find temperature also. Even otherwise, you can find temperature. How? We said it's isentropic. So I know my Pa by P1. Pa by P1 is equal to Ta by T1 to the power gamma by gamma minus 1. I can use this also to get my temperature at the exit, okay, at the ambient condition. That is also a possibility. Okay, two ways of doing this. Okay, this is the way we will approach this problem. Why did I pick this problem separately? All this time we have been considering boundary conditions as velocity vector direction. This is one problem where pressure at the exit is given. Pressure is the boundary condition given for the flow direction. Okay. Two boundary conditions are typically used in gas dynamics world. Okay. Once this is done, the next step is just to go and use this expansion fan concept along with all the previous compression wave concepts you have, all that mixed together in flow situation applications. That is the only thing left. Okay. And the way to start is by picking the simplest problem ever possible in supersonic flow. A flat plate, 2D flat plate at an angle of attack. Let us say this angle is some alpha as in aerospace terms, and I am having a uniform supersonic flow coming in, and I want to tell what will happen here. It is of course considered to be inviscid. We are still in inviscid world. So I am going to draw this one line that is going to touch this. Now this is going to help us to understand the problem. The way to approach this problem is to say I want to draw what is the wave nature at the front. If I look at this dotted line and above, then I will just block this region with paper. It looks like it's flow with a sudden expansion corner. Streamline can be equivalent to a wall in inviscid flow. We are in inviscid gas dynamics. So all I have to do is it will have an expansion fan like this. Flow will come like this and turn around like this. That is the easy part. Now a little more difficult part, I will block the other side of the dotted line. I am having only this dotted line and flow below. What is this saying? There is a wall which is coming into the flow. Okay, this is like a compression and it is a sudden change. So it is going to have an oblique shock, which is some few classes before stuff. I have to go find the angle. We hope that currently it is not a detached shock. Detached shock case is a complicated case for this problem. We won't deal with it right now. Okay. Let us say it is attached shock and I can find the beta value from there. This is my beta value. I can find it, let us hope. Okay. We can just go find the Mach number and gamma, I can get a beta value for it. So I have drawn this. Okay. Let us just change the color a little bit for the plate. Okay. Let us say that green thing is my plate, this is my shock, this is my expansion. I have drawn this, my flow field here is also parallel like this. Okay. Now the next thing to do, I have to find what will happen on the back. This flow field is going to go like this, this flow field is going to go like this. If there is no problem, they will just keep going straight like this, but that is not going to be the case. Why? Because the pressure here is going to be different from the pressure here. How do we know that? This below this dotted line region is going to go through a oblique shock, which is a compression. It is going to increase pressure here. Okay, let us mark regions. Let us call this infinity region. This is called 1, this is called 2. We can tell now that P1 less than P infinity and P2 is greater than P infinity. I can tell that for these two streamlines now. Because of this, I am going to have a case where this pressure is higher than this. When these two packets of streamlines, packets of fluids comes along the closest to the wall, when they touch, what they are going to see immediately is there is a pressure jump. What will happen? Flow will want to go from high pressure to low pressure. Now once that is said, I will erase these things. Once that is said, we can also tell that the streamline wants to turn that way because that region is lower pressure. The same reason I can tell that the streamline wants to go away from high pressure region for the low pressure streamline, that will also turn. If I say this, when will they stop turning? It will go to a point where the pressures will become equal. Consider a case where it is turning too much. What will happen? Then now that side will be finding that, oh, these guys are pushing too much without any force. A better way of explaining this is after I put the waves here. Okay. If I think about what will happen here, I will block the top side. I am having only the bottom side. Okay. I am having flow along this wall and it is now turning. I do not know by how much, let us just say it is turning, but it is turning away from the flow direction, which means it is an expansion corner. Okay. So there is going to be an expansion wave here, expansion fan here. Okay. This region is my expansion fan, let us say. If I look at the top section alone, flow is coming like this and wall is moving in. Why do I call this a wall? It is actually the streamline center line will be as if it is a wall in a inviscid flow. Streamlines are equivalent to a wall in inviscid flow. So I can just say that the wall has moved in. This is equivalent to our problem which we did some days back, this problem. So it is going to have a shock in this region. Okay. With respect to this line, it is going to have a beta value. There will be a shock there. Okay. Now because of this, what is going to happen? This shock will cause the pressure which is low to become higher, while this pressure which is high will decrease now across this expansion fan to become lower. So ideally these two waves should be such that they will come to an optimum point where they will reach the same pressure. Is that the only condition? There is one more condition needed. I told you already in gas dynamics always there are two conditions. What are the two conditions? One is the velocity vector direction, other is the pressure. We keep on repeating this all through this. Okay? We will see how it goes. Okay? We have to make sure that these two vector directions are the same, at the same time these two pressures are the same. Two conditions, two constants I have to get. What are those? What is the full delta theta here, which is same as delta nu? I have to find this, how much is the change. And the second thing is this beta angle. Two variables, two conditions. I can definitely solve this problem. Okay. But it takes a lot more effort to solve this problem. We won't solve it now. We will solve it after some time. It needs iterative procedure, okay, and we do not have enough time anyway. Okay. So this is the simplest problem I have done now. I will do one more and then we will switch on to some other case. We will go and solve more problems after that. Okay. See you people next class.